Hello everyone, can you hear me? I hope I am audible today. I just want to listen from you.
Yes, ma'am.
Yes, right? Okay, and how about my screen? Is it visible to you?
Yes.
Yes, right? Okay, I have also started recording. Good. Okay, very good. Okay, very welcome to the second lecture on combinatorics. And again, today's lecture would be elementary only. So maybe some of the topics which would be actually might be repeated for some of you. Uh, so the main agenda of discussion for today's combinatory class is only few topics. Okay, and I hope you will enjoy the topics. So first agenda is non-attacking rooks on chessboard. Okay, let me see if I can write open the board. So first topic is this one. And after that, we'll start main agenda that is basically, I hope you know already, principles of inclusion exclusion, right? That we'll see in detail with derangement and some other problems which are actually application of principles of inclusion exclusion, forbidden position problem. Okay, these are the main topics of discussion for today's lecture. Okay, first, as I mentioned, so first topic is what is what. But there is so those of you don't know how to play chessboard, I mean chess or something, you don't worry about that. We don't need to be expert in playing chessboard. We need to know some basic rules, okay, to solve some puzzles related to chessboard. So that I'll of course explain it to you. So let's consider non-attacking rooks on a chessboard. So what is the meaning of that? So I hope, I mean, almost all of you are familiar with chessboard. Let's consider this is 8 cross 8 chessboard. Okay. So we are saying two rooks, they can attack each other if and only if they lie in the same row or in the same column of the chessboard. Okay. So, for example, in this example figure, okay, you can see, is there any rook which is attacking another for this example figure? Can you see the board? I want answer from you guys.
No, ma'am.
No attack.
No attacks, right? Okay, good. So how about, okay, so in other words, so we are now going to define what is the non-attacking rooks on a chessboard. So let's say we are saying a set of rooks, which are, now you know what is the non-attacking rooks are, right? So a set of non-attacking rooks on a chessboard simply means a collection of pieces, means they are nothing but rooks, okay, which occupy certain squares on the board such that no two of the rooks lie in the same row or in the same column. So for example, this is one example of a position of a configuration where actually which is non-attacking position for all the rooks, right? You can check it. Okay, now the question is, so is it the only configuration? So let's say I have n cross n board and n many rooks are there, let's say. Okay. So for example, for this particular figure, it is 8 cross 8 board and I have 8 rooks and I gave them one position such that it is non-attacking position. But the question, I mean, of course, it might not be the only one possible position where all the rooks are in non-attacking position, right? There might be several position possible, right? Several arrangement possibles. The question is how many arrangements are possible? How many
factorial.
Non-attacking. Sorry, say that once again.
N
Yes,
factorial.
right. So that's correct answer. So how did you get it? Yeah, that's a good thing.
Um,
Yes. Who gave the answer? Please just tell me your name and maybe you can show your face. That would be good. So how did you get it? So here we are assuming all the rooks are basically identical, right? They are not distinguishable from each other, right?
yes, ma'am. So
So,
since no two
Arushi.
rooks can be in same row or column, we know
Mm-hmm.
that we'll have to keep every rook in a different row.
Right. Good.
So
Yes.
now we can focus on the columns. If
Right.
let us enumerate the columns 1 to 8, 1 to n,
Mm-hmm. Mm-hmm.
and no two rooks can be in the same column. So the permutations of this 1 to n will always give us a position
Right.
such
Right.
that,
Right.
yeah.
Right. Right. So I hope everybody followed her argument. So what he said is something like this. So you can consider, let's say I have a position ij for particular root, right? So I have n many rooks, right? I need to give them some position. As you know that each of the rows actually, so each of the rows can be given just one rook, not more than that. So I is the row number, right? And let's say j is the column number, right? So I have n many rooks, right? So I can actually give them one, then some j, 2 comma some j, right, up to some j means let's say j1, j2, right, up to n comma j, some I have n many, right, jn. So these are the, let's say these are the position of the rooks, right, which satisfy the property that none of them are in same row, right. Now we need to also ensure, as Adushi mentioned, we need to ensure that they should not occupy same column also, right. So how would you specify that? So the only way to do is something like this. You need to make sure that J1, J2, all these up to Jn, right? They are different, right? So in other words, so J1, J2, Jn, this should be permutation of this number 1 to n, right? And how many permutations are possible? That is nothing but n factorial. So that's how you actually calculate the number that you can uh, we can have n factorial many arrangement which are actually non-attacking position, right? Okay, good. Uh, Now, so these are basically where all the rooks are identical rooks. I can also ask the same question, saying, let's say all the, now I am asking the same question, means non-attacking rooks, but the rooks are colorful. Okay, colorful. What is the meaning of that? Means let's say I have n many rooks and all the rooks have some distinct color. They, now can you answer the same questions? How many arrangements are possible if that is the thing?
You
Let's say I
square.
have, right, n factorial square, right? This is straightforward, right? So you have n factorial many options, right? And each of them actually, again, you can color them. Okay, so n factorial times n factorial, you can do that. This is a straightforward question. Now, slightly generalizing the question. So these, all these questions you have, maybe you have seen before also. Now let's say all the, I mean all the rooks are not of different color. Rather, I have k many colors only. Okay, I have n many rooks, and this k is basically less. Let's say it's less than equals to n. And I am actually telling you how many rooks are there of certain color. For example, I am saying that I have n1 many rooks of first color, n2 many rooks of the second color, similarly nk many rooks of the kth color. K many colors are there, and this, if you sum up, then this ni 1 to k, that is basically, let's say, n. So now the question is the number of ways to arrange these rooks on the n by n board, so that again they are in non-attacking position. That should be equal to which number? Can you tell me? This is again elementary question. So,
N factorial squared divided by n1 factorial, n2 factorial till nk factorial.
right. So, n1, right. Everybody understood why this would be the thing, and which type of argument we are giving. So who answered this question? I didn't get it.
Manish.
Manish, can you explain why you have divided it?
Ma'am, for from the first argument, in the first argument, what we did was number each the rooks in each row as 1 to n, and then did n factorial to set the columns. So I am keeping the second part constant, but for the first part, when setting the rows for different rooks, I the number of ways this could be done is n factorial divided by n1 factorial into factorial till nk factorial. This is because there are these many different colors of rooks available.
Okay.
Should I explain it more?
Yeah, please explain it more. So I think, yeah, that would be
Since
good.
there are n1 fact first we do n factorial to arrange if these were individual colors, there would be n factorial different combinations, but
Right, right.
n1 rooks are of the same color, n2 rooks are of the same color, and so on. That's why we'll have to divide this to neutralize all those cases.
Okay. So in other sense, you let's say we have earlier what you had earlier, all the colors, all the rooks had distinct color, right? Now I am saying that I have n1 mini rooks having same color, right? So now you can't distinguish between them, right? So earlier from them actually you could actually permute them in one factorial way, but that is missing now. So you need to divide it. So division rule you need to apply, right? So that's how you got it. Good, good, good. Very good. So this is all basically the elementary concepts you need. So nothing serious concepts, I would say. But these concepts you should actually have in your mind while you are solving more questions on combinatorics. Okay, now let's come back to another. This is very, very, very much simple question. I think all of you should answer this. First question. Let's concentrate on this first question, not the second one. So let's say I am interested to know all the numbers, to be specific integers, in between 1 to 600, both are inclusive, that are not divisible by, let's say, 6. Okay, so how would you count them? So I am interested to count the number of integers in between 1 to 600, right? Both are inclusive, that are not divisible by 6. So how would you count such thing?
600
Who will
minus
answer?
number. Oh,
Right. So how many numbers are divisible by 6?
ma'am,
How
we
many?
can
Uh,
uh,
uh, 600 by 6, right? That many numbers are divisible by 6. Now you need to just subtract it. You need to use the subtraction rule. Then you will get it. Am I right? This is straightforward, right? So you have, so Manish was talking or someone else gave the answer? Who will give the answer? This is the most easiest question. Krishna, I can see Krishna, Rajdev, Harsha. Anyone can answer this question, I think, right? Harsh, will you answer this question?
Okay,
Yes.
now there are 600 number between 1 to 600, and
Right.
100 of them are divisible by 6.
Right.
So
So this,
numbers which are not divisible by 6 are 500.
right. So this. So this is basically subtraction rule you have used, right? You have
Yes.
used. Good. So now, so this is the most easy question. Now you need to answer the second question. Let's say I am interested to know all the integers. I mean number of integers that are actually not divisible by 5 and 6. Okay. Then how will you answer it?
So I think
So
the
we'll
answer
count the.
is 80. We will minus the numbers that are divisible with 30.
Divisible by 30.
Yeah,
So only 30, that is okay. So, okay, which are not divisible by 5 and 6.
5, 6,
Okay,
and 30.
5, 6, and 30 you are saying.
No,
So,
actually,
how? Dharmender is.
so we are considering both that they should not be divisible by both at the same time, right?
Ha, We are talking about, okay, I'm interested to know those numbers which are not divisible by 5. Or, I mean, so if some number is divisible by 5, I will not count it. If it is divisible by 6, I will also not count it. If they are divisible by both, then also I will not consider. Okay.
Ma'am, can I answer?
Yes, Dharmendra, please go ahead.
Yeah, so we will minus the numbers that are divisible by with 30.
So that's only the thing. So what is your answer?
Yeah, because this is like we are excluding the numbers that are divisible by 5 and 6 at the same time.
Okay. No,
If,
did you understand my question?
Am I
Did you
on?
understand? Yes.
Ma'am, first
Uh,
of all, we will subtract all the numbers which are divisible by 5, and
right.
we will also subtract all the numbers which are divisible by 6, and
Right.
then we add all the numbers which are divisible by 30.
Right. Good. So that's the answer basically. So Dharpendra, did you understand what he is saying?
yeah,
I
actually,
think.
yeah, I understood him. Actually, I didn't understand earlier your question exactly.
Acha, acha. So that's why I actually explained it twice. I am explaining it again. So the question is basically, I will not count those numbers which are divisible by 5, which if it is divisible by 6, okay, and of course, if it is divisible by both, then also I will not count. Okay. Now it
Shouldn't
makes
it be
sense.
or
Huh.
in that case?
Right, right. So maybe, yeah, divisible by 5 or 6. Yeah. 5 or 6 means 5 or 6 or both also, right? Okay, so yeah,
No,
good.
ma'am, I
So,
think it should
huh,
be and because we are counting the complement, right? So its complement will be those which are divisible, not divisible by 5 or 6.
okay, so anyway, this is just English language. Yes, that's also logic, and right, come under logic also. But yeah, so I hope you have understood the question. So now, basically, the thing is, you can visualize this. This is the set of all numbers in between, let's say 1 to 600, right? Now you have a set of numbers which are actually divisible by 5, right? This is just a Venn diagram. You have set of numbers which are basically divisible by, let's say, 6. I should color them different color so that yeah, so let's 6 divisible by 6 is this set, green wala, and the red one is divisible by 5, and there of course there are several numbers which are divisible by both, right? Now if you want to count those numbers which are neither divisible by 5 nor 6, right? So basically I am interested to look at this part of my diagram. I'm so sorry. I am interested to look at this portion, right? So basically, if you minus it out, the number which are divisible by 5, and again the number which are divisible by 6, then basically you are minusing out this green portion, this intersection portion twice, right? So that's why you need to add them. Okay, so then you will get the answer. So basically, so this is okay, this is too easy question using the Venn diagram. This type of diagram is known as Venn diagram. I hope you have heard this term before. Have you heard this term, Venn diagram?
Yes, ma'am.
Yeah.
Right, okay. So explaining this using Venn diagram for 2 or 3 types, I mean 3, say I have also, I can modify the question, right? And I can ask you the same similar question, like count the number of integers between 1 and 600, which are divisible by, which are not divisible by 6, 5, 6, and 8. Okay, I'm interested to know that. Then again, I think you can answer this, right? Now the generalized question is, I hope you have understood this, right? How you are going to do this. Let's say I have also something called 8. Then basically you need to, how will you count that in that sense? Do you have some general expression how to do this type of counting?
We
Any
can
idea?
use we can use by principle of inclusion and exclusion.
Right. So we can use principle of inclusion exclusion. What is that principle? Who gave the answer? Binay, right? Okay.
Yes,
How
ma'am.
you got this? So what is that principle?
Yeah.
I did not write the principle. Yeah. So what is that principle of inclusion exclusion?
Yeah, ma'am, we can write it is like that. Yeah. So there is a universal set X. So X minus union of AIs is equal to summation of minus 1 to the power I into AI, where AI is where AI is defined as A1 intersection A2. I mean up to I terms. There are I intersections
Okay,
of
okay, okay.
AIs.
Yes, thank you. Thanks, Bina. So, right. So you are in right direction, I would say. So, what is principle of inclusion exclusion, right? So, if you see the question which I asked here, so there is some forbidden properties I am describing, right? So, what is the forbidden property? For example, in the first question, I asked. So, the forbidden property was something like that. I am not interested in those numbers which are divisible by 6, right? So that's one property which is forbidden. Means divisible by 6 is a forbidden property, right? Similarly, for the second question, for me, I had some forbidden properties, right? For example, divisible by 5 is a forbidden property, and also divisible by 6 is another forbidden property, right? So let us generalize this concept. Oh, I'm so sorry. Yeah, let us generalize this concept uh, and name that as principle of inclusion and exclusion. So let's say I have P1, P2 up to, let's say, M many such forbidden properties. Okay, these are all forbidden properties. For what? So this is abstracting out. Okay, I am just abstracting the thing. This is known as abstraction. So in other sense, vague, right? Okay, so let's say I have a set of elements. That set I am denoting as S. Okay, so some of the element in S, they are basically satisfying property P1, right? So let us name that set as A1. So what is A1? A1 is basically all the element belonging to the given set S such that X satisfies property P1. Okay. So similarly, you can define A2, right, up to AM, right? So in general, AI is basically all the elements in the given set S such that X satisfies property Pi. I did not write property, so property Pi, just shorthand I am writing. Okay. Right. If you see the question which we asked for, we were basically interested in. So what was the question we asked? We were interested in this thing. So I don't want my elements in the given set to satisfy any of the property, right? A1, A2, up to AM, right? Sorry, right. Properties means right. P1, any of the properties P1, P2, and PM. I don't want them to be satisfied, right? So in other words, I am interested to know what is this set. I am interested to know, let's say, A1 complement. What is the meaning of A1 complement? A1 complements mean those elements in your universe, means here it is S, which doesn't satisfy property P1, right? Okay. Union, not union, it should. So intersection A2, right? Intersection A, M. This cardinality. I am interested in this number, right? For example, here for the question number 2, right, where we were interested to count number of integers between 1 to 600, right, which are not divisible by 5 and 6. So they are basically, I had two property. So property P1 stands for divisible by 5, right? Number divisible by 5, that is the property P1, and P2 was basically the property that the number is divisible by 6, right? And what is A1? A1 is basically all the set of elements, means all the set of numbers belonging to this range 1 to 600, both are inclusive, okay, such that x satisfies P1, right? Means x is divisible by 5. Similarly, my A2 is something like this, x belonging to the same thing, but x is divisible by 6. And the question asked, what we asked for is basically we are interested to know this number, all the numbers which are not divisible, neither divisible by 5, not divisible by 6, right? So in other words, you want to basically exclude A1. So all the numbers which are divisible by this, you want to exclude, right? So this you want, right? Am I right? Union, you want to basically write. So this is the number which, this is the count which you are actually interested in. Am I right? Is there any doubt of this? I did right calculation or wrong? Tell me.
Ma'am, actually you have taken the bar 2 times
So
in the above equation.
I don't know. Tell me whether this expression is correct or not.
Yes, ma'am, this one is correct.
This expression is correct?
Yes,
It is correct. Yes, right. So I am interested in counting this number. Okay. So can you tell us what would be the formula for this using Venn diagram? You already said what is that number, right? So I will be actually so this actually 600 minus. So I am actually interested to count the set A1, minusing out this, then I need to add A1 intersection A2, right? That was our formula. Am I right?
Yeah.
Yes. Okay. So that is just for A1 and A2 if I have just two, right? Two types of properties and two types of this type of sets if we define. So I have m many things. So now we are generalizing this same formula, means same question. So I am interested in this count. So I have m many such things. So I'm interested in this. So what is the formula for that? Also, if you propose a formula, you need to prove it. So not only the formula, I also need the proof. So what will be the formula? So okay, sorry, this should count, right? So what is the formula for that? Give me the formula. What would be the formula? What is your guess? You already know, right? Principle of inclusion and exclusion.
Summation of AIs.
Right.
First of all.
Summation of cardinality of AIs, right?
Then we have to add summation of AI AJ intersection.
Right, AJ.
Then we have to
Right.
subtract summation of intersection of AI AJ and AK and so on.
Right. Good. So in this way, I'll continue minus 1 to m. So right. So last one would be A1 intersection A2 intersection AM, right? So in other word, if you can see, so basically we are actually counting what is A1? A1 basically the forbidden property, number of number of elements satisfying the forbidden property 1, right? Right. So this way visualizing is, I mean, easier than saying that this is not the some set of elements is not satisfying some property. That counting is something sometimes, I mean, it is more confusing rather than counting that this property is satisfied by so many things. So you count that. So that's why people have actually define or describe principle of inclusion and exclusion in terms of forbidden properties. Okay. Okay. So now we have actually gave some formula. Now the question is why this is. Now you need to prove it, right? Why this is correct formula? Why this is correct? Why this is the formula? Can you tell me? How would you like to prove it?
We can count
Yes.
each element, like whether it
Acha.
is in the union or it is not. So
Good. Yes.
from there we
So
can prove it.
right, we can do by using that only. So let's say X is one element in that S, right? So there is either of these two possibilities. Either X is belonging to this forbidden set, any of the forbidden set, right? Means it is here, or it is not, right? These are the only two possibilities, right? Okay. So if let's say X doesn't belong to any of these AI, okay? So I belongs to this M. Then how many times it is counted in your formula? You need to show that it is counted exactly once, right? I need to count actually those elements which are not satisfying any of the forbidden property. So X is one perfect example of that. Let's say X is an element in S which satisfies none of the properties, right? So it should be counted exactly once in your formula, right? So if you see the formula, now can you see that this is counted exactly once, where it is appearing, where it is counted. So it is actually counted. We are counting only here. You can see since X is belonging to none of this AI, so it is actually here. It will be in this count. It will be 0, 0, 0. Everywhere it is 0, right? So if X is belonging to S such that it is satisfying none of the properties, we have actually correctly counted it once, right, in your formula. So for that it is correct. Okay, now how about some x, which of course it is belonging to S, but let's say X belongs to K many, X basically satisfies, X satisfies some of the properties, right? Let's say it satisfies K many properties, K many forbidden properties, which we have actually mentioned, right? P1, P2, Pm. So among those, so it can actually, it is satisfying K many forbidden properties. So you can see, so for other, I mean, if it is X is of not this type, so if it must satisfy some of the properties, right? So for the without loss of generator, you can assume that K is satisfying, so X is satisfying K many properties, where K is basically how many, so what should be the value of K? Can you give me some bound? How many, what is the range of K?
1 and M.
Right, 1 to M, right? So it could be anything, 1 to M maybe, so any of the properties, let's say, so for some fixed K. So now for some fixed K, can you show that such type of X is counted 0 times in this formula? Then basically you are done. For any value K, which is non-zero, right, means it has some value in between 1 to M, you need to show that it is in this formula, it is actually counted 0 times, right? Because we don't want to count that those type of elements in your formula, right? So if it is done, then your proof is complete. Then we don't need to bother about that. This is one way to prove the principle of inclusion exclusion. Another way to prove is by induction. So which I am not going to prove. So because this proof is, what should I say? It is much more interesting than the other one. Okay. So can you now show that if this is the case, then it is counted 0 times here? Okay. So how many times here it is counted? It is counted exactly 1 times. Now how about here? Can you tell me here
K.
how many times it? K many times, right?
K times.
So right. So here how many times it will be counted?
K choose 2.
Right. So K choose 2. So here how many times?
K choose 3. So
Right. So right. Right. So what you are getting basically, you are getting 1 minus K choose 1 plus K choose 2 minus K choose 3. So that many times it is going to be counted. up to -1 to the m k choose m, right? So that many time it might be counted. So now if k is less than uh, okay, so if k is less than m, then basically, do you know what is the value of k m?
If it is strictly less than m, then it is 0.
Right. Let's say it is strictly less than. Right. Strictly less than. That's a good point. So it is 0, right? So in other words, this formula you can actually rewrite it as 1 minus k choose 1 plus k choose 2. Then basically plus -1 to the uh, k choose k, right? And do you know what is this?
0.
This is okay. This is straightforward to say 0 because we know that it should be 0. But why this is 0?
Binomial.
By binomial, right? So you can actually write this. So we know this 1 minus 1, sorry, y to the k is basically this, right? Something here, y, uh, this term will come, right? And if you just place y, the value of y to be 1, then basically you will get this expression, right? Which is nothing but 0. So it's a binomial from binomial theorem you are getting. So in other words, we have just the concrete proof. So we have just two statements for proving the principle of inclusion exclusion. I think all of you already know this. This is a known stuff. Okay, there is nothing to say more about this. Okay. So there are actually many important applications of principle of inclusion exclusion. So we'll see them now. So for example, let's assume, so let's consider the first question. Okay. So at a party, let's say 10 gentlemen were there. Okay. So all of them were carrying their hats on their head. Now, of course, when they went there, so it's a formality that you need to, let's say, give the hat to somebody. Let's say that's the caretaker or something like that. Now, when you need to return, right, you need to take your hat back. But it might be the case that the caretaker was so much careless, you didn't get your own hat. And actually, nobody got their own hat. They got just one hat. Okay. So now the question is, in how many ways can their hats be returned so that no gentleman gets their hat with which he arrived? Okay. So this is one question. Any idea how to answer this question? Okay, if you don't bother right now to answer the question, let us see another similar question. Similar question, something like this. Let's say I have some machine, okay, and so I have many plugs. Let's say for the time being, I have 8 plugs, okay. So for cleaning purpose or something, so maybe I just open the plugs from the machine, right? So after the cleaning and all, now I need to again stick those plugs to their position, right? And let's say those plugs, I actually couldn't manage which plug where I mean from where I took up them, so I just mismanaged them, right? So it might be the case that none of the plugs were plugged to their original position. It might be the case. Now the question is how many ways it can happen. Okay, so do you understand these questions? I hope you have already saw this type of question before in your discrete mathematics course, right? So if you generalize this, so this is known as basically this type of problems are known as derangement problem. So you can generalize this as another problem, which I am just going to tell in a moment. And if you generalize that, so this is basically generalization part, right? We have many problems like this which appears in real life, and the answer to all of them are actually similar, right? So now we want to generalize how, because this is the mathematician part. So mathematicians love to abstract out, right? So they love to solve more general problem rather than small problem, right? So let's define derangement. So what is derangement? So derangement basically is something like this. derangement of a set of natural number 1 to n is basically is a permutation, okay, such that none of these natural numbers are in its original position. Okay. So, for example, let's say I am talking about I have, let's say, only 4 numbers 1, 2, 3, 4, and I have a permutation which looks like this 4, 3, 2, 1. So, of course, this is a permutation, right, of the given set of natural number 1 to 4. And you can see none of the number actually is in their own position, right? 4 is not his in position, 3 is also not, 2 is also not. So is it the only the way we can make this derangement? Okay, it's not, right? So we define Dn to be the number of possible derangements for set of natural number 1 to n. Okay, we denote this as Dn. Now the question is, so this is the number, right? So now the question is, what is the value of Dn? Can we calculate it using principle of inclusion exclusion? Okay, so that's the question. So I hope you have understood it. Now the question is, can you answer this? I mean, can you write down one expression for Dn and prove it that this is the correct expression? So what is the value of Dn? How you are going to n factorial. So you are giving the okay, n factorial then into
1
okay.
minus
1 minus
1 by 1 factorial.
Okay, 1 by 1 factorial. Then
1 by 2 factorial minus
okay.
1 by 3.
Okay, good. Who got give the answer?
Sure.
Shaura. Good. Thank you, Shaura. Right. So, okay, let me see why the direction is not. Okay. Good. You are correct. Your answer is correct. So minus 1 to the n, right? 1 by n factorial. That's what you want to say?
Yes.
This is yes. Okay, so that's your answer. Now the question is how you obtain this, right? That is the question. How you obtain this using principle of inclusion exclusion. So here that is again I am blindly. I mean, if you don't remember the formula, no worries. So we can solve this question using something like this, defining forbidden properties, right? So what is the forbidden property 1? Let us define that. So forbidden property 1 is basically so you have a permutation, so which satisfies the property 1. So what is that property? If the number 1 is placed correctly, right? Means it is in its own position, is correctly in first position in the permutation, right? So that is the property P1. So you can actually write in this way up to Pn, right? If n is placed in the nth position. So in other words, Pi is basically one property if I is placed at ith position. Okay. So you have n many positions which are forbidden, right? And so we have a set of number, right? So so what is the set of all possible arrangements, right? Set of, so this set, the universal set S, right? If you just want to apply the principle of inclusion exclusion, so you need to define S. So S is basically all permutations of the natural numbers, right? The set S is basically all permutations of
Excuse me, ma'am.
yes, tell me.
Sorry to cut you off, but will the lecture slides be uploaded?
Yes, lecture slides will be uploaded, but with a, so you can see the lecture slides. I mean, in the lecture slide, I have hardly written something. So it's just for the question. Right, PPT will be available for sure.
Okay,
yeah.
ma'am. Thanks.
Yeah. It will be available. There you will only get the question, not the answer. Okay. It will be available for sure, no worries. So I hope you have understood S, right? All permutations of this natural number is S. So we are actually interested in, and okay, so we also need to define correspondingly A1, A2, sorry, this is AI, up to AN. So what is A1? So A1 is basically all the permutation in S which satisfies property P1, right? So basically AI, you can define all the numbers X, or sorry, not numbers, this is permutation X belonging to S such that X satisfies property Pi. So what is the property Pi? Means X, in X, I is in ith position, right? So set of all permutation where this is happening, that is my AI. So now basically the derangement, the number Dn is nothing but, if you just apply the principle of inclusion exclusion, then it is cardinality of S minus sum of this AI, right, plus sum of AI intersection AJ, right, minus, you can write it, minus 1 to the n, right, A1 intersection AN, right? Okay, so you know this S, cardinality of S is already knows, right? What is S? S is all permutation of this natural number. So that is basically n factorial. Now what is this cardinality of AI? If you consider any A I, so what is that? So it says it is a permutation, right? It consists of all the permutation where ith element is in correct position, right? So if ith element is correct position, means if you see the permutation and go to this ith position, this is always fixed. This is already filled by I. Okay, so you can basically ignore. Now basically you need to see, so all the permutation which satisfies this means you need to see, so I have rest n minus 1 many elements, so how many ways you can permute them, right? So the cardinality of AI is basically how much? Can you tell me this, that number? Cardinality of AI?
N minus 1 factorial.
Right, n minus 1 factorial. And this is same for all the AI, right? So how many of them are here? So this is n choose 1, many of them are there. So that's why you can write it n choose 1 times n factorial, right? Similarly, how about this thing? This thing, it is says AI intersection AJ means ith and jth position are fixed by I and j. So you have n minus 2 many remaining positions are there. You need to fill up. You need to how many ways you can actually permute them. So that is basically, so if I and j position is fixed, right? So I have n minus 2 many numbers, and they can actually fit in this many ways, right? This many permutation we might have in minus 2 many permutations, right? So the second term would be n minus 2. Oh, I did not write it correctly. Okay, clearly, otherwise you will be confused. Okay, so this minus, so this is basically, as I already mentioned, in choose 1 n minus 1 factorial way. The second would be basically n choose 2, right, times n minus 2 factorial way. You can do this, right? Am I right? So in this way, if you see, basically the argument follows straightforward way, n minus 3 factorial plus blah 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 plus minus 1 to the power n, and then the last term. What would be the last term? Can you tell what would be the last term? How many ways you can do that? All the elements are in their position, right? So, right? So it means you can do this only one way. There is no other. So this is your formula, right? I mean, just if you apply the inclusion exclusion principle, you will get this formula. Straightforward. Now, basically, it is straightforward to see this. This n choose 1. So they are basically, I have in the denominator n minus 1 factorial would be there, one along with 1 factorial, right? Of course, in the numerator also you have n factorial. So you can write this n factorial by 1 factorial. So the second term, I can write this by this. Third term by this. Now you can see basically minus 1 to the n. Okay. Hmm. Right. So let's write this as 1. No problem. So now if you see the formula which I forgot who proposed, Shora proposed, right? Shora proposed the formula. Then it is basically the same formula which we are getting. Minus 1 to the n, 1 by n factorial. Right? That's it. So this is the derangement. Now you can see, if you go back to the question which we asked earlier, this basically, what is the answer for the first question? Can you tell me? So I have 10 gentlemen, and how many ways it can happen that no gentleman got their own hat? How many ways you can do this? Okay, how many ways you can do this?
D10.
Right. So it is D10, right? Okay, very good. Right, D10. And how would the second question? So it would be D8, right? So you have actually more general thing, which you have generalized as derangement problem, and you can, using that formula, you can actually solve many things. Okay, very good. Now again, I am going back to some, I should say, very trivial question, which all of you should answer. Okay, now let's consider this question. Let's say again, at a party there are n men and n women. Now the question is, how many ways can the n women choose their partners for the first dance? Let's answer this question first. So let's say they are going to dance, okay, in the party. So there are n men and n women. So same number of men and women. Now the question is, how many ways they can choose their partners to dance?
N factorial.
N factorial, right? Everybody convinced that this should be the first answer should be n factorial?
Yes.
Yes, right? Now, okay, yes. Arushi said something else? Okay, good. So you have the answer. That n factorial way they can actually make their pair, right? Okay, now the question is, how about, let's say the first round of dance is complete. Now second round of dance will be started. Now before that they need to change their partner. Okay, but of course they should change their partner in such a, of course it should not be the case that someone was playing with the same partner. All of them should play with some different partner for the second round. Now the question is, how many ways it is possible?
DN.
DN.
Right. So it's straightforward, DN. Good. So you have the very good answer. Okay. Now let's. I again answer again. Again, it's a party problem. Okay. And in the party again we have n men and n women. Okay. And what is the thing? So here again. So before going to the party, they submitted the hat to the caretaker. And when they, okay, so there is some distinction. So now the male hat and female hat are different. Okay, they are not of same type, let's say, that one can distinguish. So when they will return, the caretaker will give male hat to male and women hat to women. So yeah, that, I mean, in this, caretaker is not that much careless, but it might happen that no men got their own hat and no women also get their own hat. So now the question is, how many ways it can happen? Can you tell me?
square.
Dn square, right? Okay.
You can just
So
multiply the.
so you have multiplied this, means you have applied the principle of multiplication. Okay. Good. So these are all elementary things. There is nothing new in it. Okay. Good. Now let's come back to some question which is known as forbidden position problem. This is also, you'll love it. So I am so sure, and you'll be able to answer it maybe. So now first let's listen to the story. So what is the story? So we have, let's say, 8 boys, and they are all school children. Okay. So maybe they stay in some residence or something. Maybe they are residing in hostel. Maybe you can consider boys of IIT, Delhi itself. 8 boys are there. and in each morning, every morning they go for a walk, okay, together. But they don't go side by side, rather they prefer to go by making a line, okay. So they go by line. So in other sense, somebody would lead so there should be one leader and rest of them will follow, right? But okay, so they are actually smart boys, means like you only. So what they prefer, they don't want to see the same person at their front each day. Okay, okay. The next day, whatever the next day, let's say first day, these were the boys 1, 2, 3, 4, 5, 6, 7, 8. So maybe boy, girl, anything. Okay, so 8 friends. So they were like this 1, 2, 3, 4, 5, 6, 7, 8. These are the number, let's say, attached to them according to the way they actually went for a walk on the first day. Okay, so next day they decided that okay, it should not be the case that okay, there's two. We'll see the guy one at the in front of him, or three should not see two in front of him, right? Okay, similarly, 4 should not see 3, 5 should not see 4, 6 should not see the guy before him, means 5 in front of him. In this way, right? I hope you have understood. Now the question is, how many possible positions could be there so that this is possible? This property is satisfied. So for example, if it is in the next day, if we decide that this is the possible arrangement for the walk 8, 7, 6, 5, 4, 3, 2, 1. This is of course one permissible position, right, which the boys want, because you can see 8 is the leader. So he last day he saw 7 in front of him, so today he is seeing nothing, so it is all right for him. 7 also is not seeing 6, so that is okay for him. 6 is not seeing 5 in front of him, so it is right for him. 5 is not seeing 4, that is okay, all right for him. Similarly, it's you can verify that everybody is satisfied, right? So is it the only way to arrange them? Is it the only way to arrange them? Is it the only way? No, right? So the question is, so how many ways you can arrange, right? That's the question.
D8.
DN?
D8.
D8. Okay, why D8?
It's like we can see one is related to 8. The first person can be related to the last person. And for every other position, we can relate it to the one after it. So in that sense.
It is D8. I did not get actually it is not D8. But yeah, can anyone else? So it's 10. I mean, it is not D8. It's not derangement, right? We're not saying that one should not come at this position next day. I'm not saying that, right? But I'm saying that it should not be the case that 1 and 2, this is coming like this, or 2 and 3 are sitting like, they are coming like this. This is forbidden. 2, 3, this thing is forbidden uh, in your uh, line. 2, 3, this position is forbidden. 1, 2 is forbidden. 3, 4 is forbidden. 4, 5 is forbidden. 5, 6, that should not occur in your line. 6, 7 should not be there together. Similarly, 7 and 8 should not be together. Yes.
Yeah,
can we relate
D7,
it to
D7
Yes.
plus 7 D6 maybe the answer. Like
D,
we can
uh-huh.
we can think
D7,
that if plus 7 D6 plus
D7
7
plus
times
D6. Oh,
7
7
times
times.
D6.
Okay. Okay. Why? You need to give a proof.
Ma'am,
Okay.
yes, ma'am, I am giving. Yeah, like first
Okay.
of all, we can the case one is like one is the leader. I mean, one is in the top place
Right,
position.
right.
Then all the 7 will be dearranged. So from there it will be D7. And
so you are saying that okay, 1 was the leader. Yes. Then
yeah,
what?
and after that, yeah, like two, like, and every person is related to its, I mean, predecessor. Like 2 is related to 1, 3 related to 2. So in that case, the 7 will be dearranged. So
7
it
will
will be
be
like this.
rearranged. Okay, so these
Yeah.
all these guys are rearranged. Okay, they
Yes.
are not in their position. That's what you are saying. Okay.
Yes, ma'am. Yes, ma'am.
Mm-hmm.
So it will be D7, and after that we can take like any of the seven will be the leader. So seven times, and then like like if for without loss generality we can assume that like two is at the front. So we can say
2
that like
is
two at the top, I mean leader of that,
2 is
and
top. Then
yeah, and
then
like one can be at any place he wants, there is no issue, and other six should be dearranged, like they should not be in that same order in the like the
I did
first
not
one.
get I did not get the answer clearly. Okay, so
Ma'am,
maybe
is it
so
8d8? Is it
8
8d8?
d8.
N
8 d8.
factorial,
No, that is also not the question. N factorial.
8 factorial.
N factorial times 8 factorials.
No, ma'am, only 8 factorial.
Ah, so you are saying it is only 8 factorial, then something else? Only 8 factorial you are saying.
Yes, ma'am.
Only 8 factorial. How you got this? It's not correct answer though. So okay, so I missed somebody. I mean, who said this D7 times 7? I mean, you are very close, though you are not correct, maybe. But I did not get the argument also clearly. So maybe try to write your answer. Okay, so I will check it. Write your answer, send me. So it's though it's not correct, but I am wondering if one can, because there is
Should
some
it be
relation. Right?
7 plus
Yes.
49 d6?
7 plus 49 d6.
From
How you
d7.
got this? D7.
No,
Why?
the front one is d7. The,
Ah, okay. I mean, answer. Okay, so try to. Okay, you are. Why are you mixing with D?
no, it's d7 plus 49 d6.
D7 plus. Okay, you are saying that D7. Okay, D7 plus 49 D6. You need to give a proof. Okay. You need to give a proof. I mean, without proof, I can't say that this is correct.
It's basically the same thing the above guy said about
Okay.
d7 plus 7 d6.
D7. What is the logic? Okay, you
Because
tell me the logic.
like first he has kept the leader fixed
Leader is
in
fixed.
the
Okay.
first case. So suppose the leader is 1, then the leader will remain 1 in the
Leader is
second
remain
part also.
one.
So in that case, it's d7 only. They just
Okay, just okay, just a minute. Let me see the okay, and other guys are dearranged. Means okay, they can if they can jumble their position. So why do you think that it will be one valid position? Because let's say I have 3, 4, then this is 2. Then let's say this is a jumble, right? But 3, 4
Yes.
can come like this. So how you are getting this D7? I don't understand. Right?
And
So
like
this is
we
not correct
can
answer. Huh.
Yes.
So that is
like
not
in for the
correct.
D7, yeah, like for D7 part, like we are
Mhm.
like two is related to three, three is related to four. So
Okay. But
yeah.
so D7, so you got it right. So that way you cannot fix the position of one. Then you can't say that this is a dearrangement, right? Because you can see, I mean, you in that dearrangement, if I can fit 3 and 4 together, right? They might not be in their position somewhere else, but 3 and 4 might come together. So in this way, I don't see any argument, though, and it is yes. Someone is
77.
Priyanka, yes, what you are saying? What is
7d7.
7 times D7? Priyanka. Okay, why?
Yes, ma'am.
So, what is the argument?
So, initially, when it's 1 to 8, we can just put for 8, 7, 7, 6, like we can just pair them up. And finally, the last one will be 2, 1. So, for each of these 8 to 2, we'll be having D7 as the dearrangement. Like the numbers from 7 to 1 will be shuffled. Now, any of these combinations, like any of these can be the leader. So that will turn out to be 7 times.
I did not understand. I mean, did you see that in the rearrangement it might, so 2 might not be in 2's position, but it might be in some different position. 3 also might be, but they can come together, right? 2 and 3 might come together. So you can't prohibit in such a way. I
Ma'am,
don't see any. Yes.
ma'am, we could use the principle of inclusion exclusion.
Yes, yes, that's the natural thing to do. Yes, you
So,
just use, right? Yes, go ahead. Who is
so
saying this?
first we would
Subhan.
so first we would count the number of arrangements
Huh?
in which 2 follows 1, like 1 2.
Right. So basically, if you want to apply principle of inclusion exclusion, then basically you need to define the prohibitive property, right? What is your prohibitive property 1? So Shubhan, can you tell me what would be the prohibitive property 1?
Like 1 and 2 are in a
Right.
line basically.
Right. So basically, the property 1 is basically that property. Those arrangements where 1 and 2 come together, right? They goes like this together. Together means 1, then 2. Okay, that in that order. So that is the prohibited property I am defining as P1. Similarly, you can define P2 where basically 2 and 3 goes together, right? So in this way, how many properties you can define?
7.
Right. So right. Let's say okay, good. So Pn minus 1. So I'm generalizing it since we are mathematician, right? So we are very good at generalizing. So what we are now we are giving this as some number like Qn. I am sorry, similar to Dn. I am defining one number called as Qn. So which will give you this specific answer. What is this? So this is basically it is that number for each positive integer n. Let Qn denote the number of permutation in which none of the patterns 1, 2, 2, 3, 3, 4, then n minus n, n minus 1 comma n, they actually occurs. So right. So let's define that as Qn. So Qn is the number of all permutations, okay, of the natural number 1 to n, where 1, 2 will not occur, 2, 3 will not occur, n minus 1, comma n, that will not occur. So these prohibited things will not occur. So that number is Qn. Okay, so and we are interested to know what is the value of Qn. Okay, so as Subhan pointed out, we can actually solve it via using principle of inclusion exclusion, right? Okay, so this is n minus 1, n goes together. Okay, so now can you tell me, so what would be the formula using principle of inclusion and exclusion? Now this is easy, right? So we are basically interested in, so what is S here? So S is basically all permutation of your natural number n, right? So S is the set of all permutations of the natural number 1 to n. This, okay. So using principle of inclusion exclusion, Qn, the thing which we define, this is nothing but S minus, you know, right? Now this is very easy to you, plus this AI intersection AJ. Now you need to quickly say what is this going to be. I have n minus 1 many things, right, in my pocket. So minus 1 to the n minus 1. N minus 1 things are there. So A1 intersection A2, blah, 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 up to an minus 1. Right? So these are the properties I defined. Similarly, I need to define the sets corresponds to P, the sets corresponding to the property P. Right? So the similar way you can define, I just keep that step. I have n minus 1 many sets. So AI means those permutation, set of all permutation that satisfies property Pi. Okay, a similar way we have defined that. So this, now can you tell me what is this? Of course, the cardinality of S is n factorial. Now can you tell me what is this going to be? So what is A1, cardinality of A1? What is A1?
n minus 1 into n minus 1.
Right. So basically, if you see A1, they are basically all the permutation where 1 and 2 comes together. So you can consider 1 and 2 to be one symbol, right? And you have the rest of the symbols are like 3, 4 up to n, right? So now the question is, so how many ways you can permute them? That is basically n minus 1 factorial ways. So the cardinality of A1 is n minus 1 factorial. Similarly, cardinality of AI would be n minus 1 factorial, right? Okay, and how many of them are there in your hand? How many of these AIs are there? You have only n minus 1 many, right? So this should be n minus 1, choose 1, then n minus 1 factorial. This is the second term. How about this term? Can you tell me what is that? A1, so AI intersection AJ, right? That we are interested in, counting that. So what would be that? So let's say, so there actually two possibilities are there. For example, let's say I have this I and AJ, it might be something like this. Let's say AI is basically A1 is there. So this is this 1 and 2 should not come together. And let's say I have the 3, this is like 3 and 4 should not come together. If that is the case, I and J are like this, they are not common, right? There is no common 1, 2, 3, 4, they are all distinct in this A1 and A3. Then cardinality of A1 intersection A3, you can count is something like this. I have, this is one symbol, this is another symbol, right? So, and I have n minus, how many symbols are missed? So how many symbols you have right now? So you have one, this is one symbol, right? 3, 4, they are also coming together. You can consider this as another symbol. And other remaining, how many things are there? Remaining n minus 4 things are there. So in together, you have n minus too many symbols, right? And how many ways you can permute them? So that answer is n minus 2 factorial, right? Okay, so if AI and AJ are such that there is no common elements like this, then basically the cardinality of AI intersection AJ is n minus 2 factorial. Agreed? So now let's say AI and AJ are something like this. So A1 is, you know, that where A1 and 2 will come together. And let's say AJ is such that there is some common. So let's say this is 2 and 3, right? So in such case, if that is the case, you can see it only happens 1, 2, 3. This all, this whole, these guys are coming together, right? And I have remaining n minus 3 many symbols, right? So together with this, I have basically n minus 2 many symbols. Now the question is how many ways, if you want to count A1 intersection A2, that number, then basically how many permutations you have where using n minus 2 many symbols, right? And that number is again n minus 2 factorial. So in both the cases, you have n minus 2 many 2 factorial way you can do this. So that is good for us. So in other words, this second term is basically, you can write it as also n minus 2 factorial, right? This count, and how many such things are there? Can you tell me? You need to multiply also, right? With which you are going to multiply? How many? Right, not NC2. So that would be because n minus 1, choose 2 would be there. Right, because I have this number of properties are n minus 1, right? And number of sets are also n minus 1. So that is the reason you have this. So, okay, similarly, actually this idea, whatever I just mentioned, the cardinality of A1, sorry, AI intersection AJ, irrespective of whether there is some common element or not, this count is n minus 2 factorial. Okay, so similarly, one can say irrespective of if you have, let's say, AI AJ up to, let's say, AK, sorry, intersection AK, then this cardinality will be, one can show with similar logic that it will be how many things? Your guess? How many things will be there? I did not write it. You need to write. One can show that it would be basically n minus k factorial. Okay, this cardinality, irrespective of whether they are common or there is some plugged into or not. So this number is n minus k factorial. So in other words, if you just want to fill this, then it would be, so n minus 1 choose 3, n minus 3 factorial way, plus dot dot dot, then plus minus 1 to the n minus 1, times this, right, n minus 1. So that would be basically, what is that number? That is basically n minus 1. So that would be 1, right? It is just 1. It is just, last term is just 1. So this is your formula for Qn. Did you get it? Is it okay? So this is the formula you got then. You want to use some different color. Okay. So it looks similar to Dn, right? Isn't it? In fact, so try to prove this. I am not proving it. In fact, so the way you are proving, so why I was interested to know your argument is something like this. One can prove that Qn equals to Dn plus Dn minus 1. Okay. So try to prove this with counting argument or something. Okay.
Yes, ma'am.
That would be good for you. Okay. I have some, few more times. That's good for us. Okay. Is there any question on this forbidden position problem? This is, I think that is new for you. Okay, now
We could
let's
have done
come
it
back.
straight away also.
You could have done this straight away also, this dn plus dn minus 1.
Yeah, D8 plus D7.
D, but nobody told that, right? You gave me wrong answer. So try to prove this using counting argument. That is your homework. Acha, okay, now let's come back to another question. Again, related to forbidden position and related to this non-attacking rooks problem. So you saw this picture before also, the same picture. So let's consider this as a chessboard, 8 cross 8 chessboard, and the position which are marked, they are forbidden. Okay. So this is forbidden position. You can't place your rook over this position. Okay. Now I am interested in so number of ways you can place 8 non-attacking rooks in this chessboard, avoiding these positions. Okay. So can you give me the number? How you are going to count that? Oh, I should not write can. So what is the number? How you are going to count it? Is there any some formula or something? Don't go with formula. So that's the one thing which I will suggest. Don't go with formula. If you are given some problem, so start from the scratch. So sometimes formulas might be misleading. So what would be the number? Okay, now before answering this particular with particular positions and which are forbidden, let us answer this easy question. Let's say I have a rook, okay? Sorry, chessboard, 8 cross 8 chessboard, okay. Or maybe let's say how many? 4, maybe 5 cross 5, 3, 4, 5. 1, 2, 3, 1, 2, 3, 4. I need one more. So this is okay. Okay, now let's say I am defining these are my forbidden position. Okay. Now, can you tell me how many ways you can place your rooks in non-attacking position, of course, uh, in this chessboard, avoiding this position? Can you give me the
D8.
count?
D5.
D5. Can you give me proof why this is D5?
Basically, we are writing down a permutation of numbers from 1 to 5, which will be the row numbers for all the rooks in each column. And we are not allowed to place the ith rook on the ith row.
Right. So this is D5. Good. Now try to prove this. What would be the number?
D8.
D8. Why D8? Check it. I'm not telling you the answer. Why D8? If it is
Same
D8,
logic.
you need to same logic. Okay, why this is same logic? So here one is not.
Write
So
the
there you
numbers.
said okay. Right. So this is the position. You need to prove it. So you can actually prove with similar logic that maybe the same formula D8 you will get. Okay. Try to prove this. Maybe this is the homework for you. Try to prove or disprove whether this is D8 or not. Okay. Prove or disprove. I'm not saying, and this is a puzzle for you. So this you can see they are actually in that position. That's why you told that this is D5. Prove or disprove that number of non-attacking arrangement in this board is D8. Prove or disprove. Okay. Okay. Do you have any other questions? So this is all about elementary thing, I think. So next class, we can actually straightforward go to the next topic, which would be new to you. Any question?
Ma'am, what if
Yes.
we can attack in diagonal direction as well?
Tell me, I didn't understand who Dharmendra, right? Yeah.
Yeah.
So what is your question? I did not get you.
How can we count the number of bays if they can attack in diagonal direction as well? Like diagonally they are attacking.
Diagonally they are attacking. So yeah, so diagonal attacking. So if you okay, so that I did not say that is attacking position. So according to our definition, so which we said that one rook will attack another rook. So if that's a good question. Yeah, okay, you are modifying the question you are saying, right? If you allow this that diagonal position is also they are going to attack. Yeah, that's a new question. Means it's not same question. That's good. Good that you pointed out. You do the same question and ask the same question for the basic problem like this. So you are going to define. You are going to actually redefine it. That's welcome. And calculate this number. Okay. So what we calculated over here and see the number what you are getting. That is another question. So I hope you will be able to answer this. It's not difficult question. Okay. Try to see that. What is the answer with small examples. Okay, now there is one reference for all the things which I covered today. Chapter 2.4 from this book and chapter 6.1 to 6.5 from the same book. Okay, I think this book we also followed during our discrete mathematical structure when we studied this, the same book. Okay, any other question? Thanks, Dharmendra. This is a nice question. I liked it. Yeah, play the same thing with what Dharmendra saying that attacking rooks is not only attacking in same row, same column, but in diagonal also. Of course, the problem would be more difficult. Okay, it's not simpler like that thing. It would be much more difficult only. Try to see with small chessboard what is the answer you are getting. Okay, good. Okay, is there any other question? Any other question you have? Do you have any other question? If not, so let us conclude today. So we have learned what? Mainly we learned basic concept like principle of addition, right? Multiplication, subtraction that we have used, and also principle of inclusion, exclusion, right? And we have learned derangement and how to use principle of inclusion, exclusion to solve some forbidden position problem, right? Okay, good. If we don't have any other question, we can actually stop today's discussion. We'll meet again next Monday, right? Our regular lecture is Monday is not a holiday this day. Yeah, so we are going to meet on Monday. Okay, if no question, we can actually stop today's lecture. Thank you guys.